Good morning, everybody. Hope you're all healthy and safe. So today let us continue with the chapter 10 Banach algebra of the third module. So we have already discussed what is a Banach algebra, and we have discussed some properties related to it. Now in this lecture we are going to begin with the concept of ideals. Okay, so we have already you guys must have already learned in your algebra what is an ideal. We shall look into some properties of the ideal in this lecture. So first let us just recall what is meant by the ideal. Ideal is actually, if you are considering the Banach algebra script A, then ideal is denoted by I. It is a subspace of the Banach algebra that we have, such that what are the condition for x belongs to I and y belongs to script A, xy, that is their operation which is performed, should belong to I. This is the condition of the ideal. So this is an if and only if condition. The set I is a subspace which is a subspace of a script A Banach algebra, which is here we are dealing with commutative Banach algebra. Okay, so this is commutative. Then we say that I is an ideal if for every x belongs to I and y belongs to A, xy should belong to I. Okay, and there is one more definition, that is what is meant by the proper ideal, right? What is a proper ideal? A proper ideal is something which is I should not be equal to script A or I should not be equal to 0. So ideal is a set which is in the commutative algebra, and the proper ideal is the one such that it is not equal to the algebra, Banach algebra that we are considering, or it is not equal to 0. So this is I have just revised what is an ideal. So next we shall discuss about some remarks related to the same. Okay, which is dealing with the concept of ideals in case of Banach algebra. So the first one is if the inverse of the element xy exists, okay, then both we can say that both x and y will be invertible. Okay, so that is if we have the product of an element is invertible, product of two elements of the ideal is invertible, then they both individually will also be invertible. Okay, then what is the next one? The next one is that if x is invertible if and only if it does not belong to any proper ideal. Okay, so we know what a proper ideal is. So the second remark is x is invertible if and only if it does not belong to any proper ideal. And what is the third one? Third one is if I is a proper ideal, then so is its closure. Okay, if I is an ideal, then so will be its closure. So let's look into these remarks one by one. So the first remark is if xy is invertible, then both x and y are invertible. Okay, so this is what we have to prove. Now xy is invertible, so let xy inverse be the inverse of xy. This implies xy into xy inverse is equal to the identity element, right? So I am going to replace this, or because of the associativity of algebra, xy inverse is again E. Okay, and also by the commutativity we can say that y into xy inverse, so x is also E. So from these two conditions, what do I get? x inverse is equal to y into xy inverse. Okay, so that is x is invertible. X into this product is equal to e. So x is invertible. So similarly, we can get y is invertible by applying commutativity from the very beginning itself. So if xy is an invertible element, then both individual elements x and y will also be invertible. Okay. Now let's move on to the second remark. What is the second remark that we have? That is it is an if and only if condition. X is invertible. X is invertible if and only if x does not belong to any proper ideal. Okay, so suppose that x is invertible. X be invertible, then we need to show that x does not belong to any proper ideal, right? And let x belongs to the ideal, say I. Okay, so as x is invertible, x inverse exists, right? So x is an element of I and x inverse is an element of script A. So by the definition of I, x into x inverse will belong to I, right? This is by definition of ideal. By choosing x element of A and x inverse belongs to script A. So from this, what do I get? I get E is an element of I. Okay. So if E is an element of I, then I'm going to conclude that I is equal to script A. How can you say that? If E is an element of I, for every x element of script A, x into E should be an element of I by definition of an ideal. So this implies x is an element of I. So script A is contained in I and I is already contained in script A, so we get I is equal to script A. So if x is invertible, then we can say that E is an element of I, and so I is equal to script A, and therefore I is not a proper ideal. Okay, so if x is invertible, x does not belong to any proper ideal. Now conversely, we need to show that if x does not belong to any proper ideal, x is invertible. So what I'm going to do is, let us suppose x is not invertible. Okay, x is not invertible. That is a negation. We are going to prove the negation. So x is not invertible, and let x belongs to some ideal, say I. Okay. Then E does not belong to I. Why is that? Because if E belongs to I, okay, then for some y belongs to script A, xy will belong to the ideal. By definition, x is an element of I, y is an element of script A, so xy is an element of I. Now xy is an element of I, so I can write E is also, if suppose E is an element of I, this implies xy, I can say this is E, say E is an element of I. Okay, so I get xy is equal to E. This implies x inverse exists, right, which is a contradiction to the assumption that x is not invertible. So E is not an element of I, so this implies I is not not equal to A, right? I is not equal to A, or I can say that I is a proper ideal. So if X is not invertible, then X belongs to I, which is a proper ideal. So I hope you are getting the idea of this. We have proved the negation, that is X is not invertible. We have assumed that X is not invertible, and assuming that X is an element of I, then we can say that E does not belong to I, because if at all E belongs to the ideal I, then it will contradict the fact that X is not invertible. So I has to be a proper ideal. Now let's see the proof of the last remark, that is I is a proper ideal implies its closure is a proper ideal. Okay, so first we shall prove the concept that if I is an ideal, then I closure is also an ideal. The proper thing, it comes directly from that. First we shall show that if I is an ideal, so is I closure. Okay, so let X belongs to I closure. So by definition of closure, there exists a sequence, say Xn, element of I such that Xn converges to X. Now Xn is an element of I. I'm going to choose Y to be an element of script A. This implies Yxn is an element of I. Okay, and Yxn converges to what point? Yx, right? Because Xn converges to X, so Yxn converges to Yx. And if Yxn is an element of I and it is converging to Yx, implies Yx is an element of I closure. So for X element of I closure and Y element of script A, Yx is an element of I closure. So if I closure is also an ideal. And the proper concept, if I is a proper ideal, it just directly implies that I closure is also a proper ideal. Okay, so these were the remarks that we have discussed about the ideals, and we shall be using these remarks to just prove some theorems. So just go through the remarks and see if you have any clarifications. Just go to the proof. Everything is simple only. So that's it for today's session. Thank you. Stay safe and stay healthy.